Hey everyone, and welcome back to AI Paper Podcasts. Today we're diving into a paper that's making waves in the world of AI agents, and trust me, this one's a game changer.
Yeah, it's really interesting work.
Imagine a world where your AI assistant isn't just scheduling meetings, but actually navigating complex digital landscapes like a pro, completing multi-step tasks across various apps just like you would.
Yeah, it's the kind of seamless integration we've always dreamed of, and this paper from Apple researchers is taking a giant leap in that direction.
The paper we're dissecting today is titled Reinforcement Learning for Long Horizon Interactive LLM Agents. And let me tell you, it's packed with insights.
It is.
They introduce a novel algorithm called LOP, which stands for Leave One Out Proximal Policy Optimization.
Yeah.
Now, I know that sounds like a mouthful, but stick with us because we're going to break it all down.
We will.
In a nutshell, LOP empowers large language models, or LLMs, to become super efficient interactive agents in digital spaces.
Right. Think of it like giving your LLM the ultimate training course in using apps and APIs to get things done.
And get this, they put LOP to the test on a benchmark called App World, which simulates a whole bunch of everyday apps like email, payments, music players, you name it.
Right.
The results. Well, let's just say LOP absolutely crushed it.
It's true. LOP outperformed all the baseline models, including some of the heavy hitters out there.
Yeah.
It even surpassed the much larger OpenAI o1 agent by an impressive 9 percentage points.
Yeah.
That's a significant margin and speaks volumes about LOP's efficiency.
For all you AI researchers and ML engineers out there, this paper is a must-read.
Yeah, definitely.
It pushes the boundaries of what's possible with LLM agents and showcases the power of reinforcement learning for training them.
Absolutely.
In this deep dive, we're going to unpack the key concepts of the paper, explore the intricacies of the LOP algorithm, and delve into those fascinating behavioral patterns it produces.
Okay.
Oh, and we'll definitely discuss why it's so effective, even with limited training data.
Yeah, that's a really interesting part of this.
Ready to get started?
Absolutely.
Yeah.
Let's dive in.
All right, let's unpack this. The core problem the researchers are tackling is that current LLMs, even those fine-tuned with instructions, often struggle with complex multi-step tasks in sophisticated digital environments.
Yeah.
They just don't generalize well-meaning that they can't apply what they've learned to new situations as effectively as we'd like.
Right. Think about it for a second.
What?
An LLM might be able to follow a simple instruction like send an email, but what happens when the task involves multiple steps, like searching for specific information, making decisions based on that information, and then interacting with different APIs to achieve a final goal?
Right.
That's where things get really tricky.
So what's their solution?
Well,
They propose training these IDAs or interactive digital agents directly within their target environments using reinforcement learning.
exactly.
Instead of just feeding the model a bunch of text,
Yeah.
they let it learn by actually experiencing the consequences of its actions and getting better over time.
It's kind of like teaching someone to ride a bike. You can explain all the mechanics, but the real learning happens when they actually get on the bike.
Yeah.
Try to balance, maybe fall a few times, and eventually figure out how to ride smoothly.
And that's where LOP comes in.
Right.
It's rooted in a popular RL algorithm called Proximal Policy Optimization, or PPO, but with some clever tweaks that really make it shine.
Yeah, they've incorporated a leave one out baseline estimate, which helps the agent learn more efficiently from its experiences, and per token clipping, which ensures the training process remains stable and doesn't go haywire.
Right.
Think of per token clipping as a safety net during training.
Okay.
It prevents the AI from making drastic changes that could derail the learning process, ensuring steady and reliable progress.
Now, before we get lost in the technical weeds, let's talk about App World.
Okay.
Why is this particular benchmark so important?
App World is a fascinating benchmark because it mirrors real-world scenarios.
Okay.
It tests the agent's ability to reason, gather information, and make decisions in a way that goes beyond just understanding language. It's about understanding how to use language to interact with the digital world.
Right.
Remember, we're aiming for AI agents that can seamlessly integrate into our digital lives.
It simulates a user's phone with 9 different apps. Things like email, calendar, music player, even a payment app.
Right.
Each app has its own set of APIs, those interfaces that allow different software components to talk to each other.
Yeah.
And the tasks are designed to be pretty challenging, requiring the agent to figure out complex sequences of actions to achieve a specific goal.
Imagine the agent needing to send money to someone based on information tucked away in a text message.
Oh, wow.
This involves understanding the message, extracting the key details, finding the right person in the payment app, and then executing the transaction.
Okay.
It's a simple task for us humans, but quite a complex feat for an AI to pull off autonomously.
And as we mentioned earlier, LOP blew the other models out of the water on AppWorld, achieving state-of-the-art results on both test sets.
It really highlights the power of training agents directly in their target environment, rather than relying solely on pre-training or fine-tuning with static data sets.
Yeah.
This hands-on approach seems to lead to a much deeper understanding of how to navigate and solve problems in a dynamic digital world.
But here's where things get really interesting.
Yeah.
Through this RL training with LEK, the researchers observed some truly fascinating emergent behaviors in the agent.
Yeah.
It started doing things that weren't explicitly programmed, but that made it much more effective at solving those tricky tasks.
Yeah.
Almost like it was developing its own problem-solving strategies.
Absolutely. One of the key things they observed was that the agent shifted away from what we call open-loop control.
Okay.
Instead of trying to submit multiple code cells all at once, hoping everything would magically work out, it became much more interactive.
So instead of barreling ahead, it would pause, assess, adjust its approach, just like a human would when tackling a complex problem.
You got it.
Okay.
It's a much more intelligent and adaptive way of interacting with the environment.
Another behavior that really caught my eye was the agent's ability to consult API documentation.
Right?
Remember, AppWorld has a whole library of different APIs.
Yeah.
Each with its own set of rules and parameters.
Yeah.
The agent figured out that it could save itself a lot of trouble by actually reading the documentation before attempting to use an API.
Yeah.
Almost like it was doing its research before jumping into a task.
It's a classic example of measure twice, cut once.
Yeah.
By taking the time to understand the tools at its disposal, the agent was able to avoid making costly mistakes and came up with more efficient solutions.
Pretty impressive.
All right.
Pretty impressive.
Absolutely. And perhaps the most human-like behavior of all was the agent's ability to make fewer assumptions.
Yeah.
Early on, it would often make these leaps of logic, like assuming that everyone in the user's contact list was also a friend on the payment app.
Yeah.
You can imagine how that led to errors and task failures.
Right, because in the real world, these assumptions don't always hold true.
People have different social circles, different accounts, different ways of organizing their digital lives.
Yeah.
By learning to avoid these unwarranted assumptions, the agent became much more robust and reliable.
So instead of jumping to conclusions, it learned to actively seek out and verify information, making it much more accurate and less prone to errors.
Yeah.
And finally, it got better at dealing with setbacks.
Okay.
Early on, if an API call failed, the agent might just give up and move on to something else.
That's a very human reaction. Sometimes we get frustrated and just abandon a task.
Yeah.
But after training with LOP, it learned to persist and debug when encountering these errors, much like a programmer would when they hit a snag in their code.
It's like it developed this resilience, this ability to learn from its mistakes and keep trying until it found a solution.
All right.
Now, one of the big questions that comes up when we see these results is this.
Yeah.
Why is RL so effective, especially given the relatively small training data set?
That's a fantastic question, and the researchers offer some intriguing insights. One key reason seems to be the diversity of rollouts produced by the LLM during training.
Okay.
Now, a rollout is basically a complete run-through a task from start to finish.
Right.
What they observed was that even late in training, when the model was already performing well, it was still coming up with a variety of different ways to solve the same task.
So even though it was working with the same limited data, it was finding new ways to use that data, new connections, new ways to apply its knowledge.
Precisely. And this diversity had two major benefits.
Okay.
Early on, it encouraged exploration, which helped the agent discover more effective solutions than it would have found if it had just stuck to a single path.
Right.
And later in training, this diversity helped prevent overfitting, which is a common problem in machine learning where a model becomes too specialized in the training data.
Overfitting meaning?
It's when a model learns the specific example so well that it can't generalize to new unseen data.
Oh.
It becomes a bit too rigid. But by maintaining this diversity of rollouts, LOP ensured that the agent didn't get too fixated on any one solution.
Okay.
It remained flexible and adaptable, which is crucial for real-world performance.
So in essence, the agent learned to be a more creative and adaptable problem solver.
Exactly. which is fascinating when you think about it.
Yeah.
We're starting to see AI agents that not only follow instructions, but can actually think outside the box and come up with novel solutions to complex problems.
Yeah.
And all of this from a relatively small amount of training data.
Right.
It really speaks to the potential of reinforcement learning to unlock new levels of intelligence and autonomy in AI systems.
Now let's shift gears a bit and dig a bit deeper into the LOP algorithm itself.
Okay.
What sets it apart from other RL algorithms out there?
Well, as we touched on earlier, it's built upon PPO,
Right.
which is already a powerful and widely used RL algorithm.
Okay.
But the researchers made some key modifications that really amplified its performance for this specific task.
Okay, so let's break down those modifications. What makes LOP so special?
One of the key innovations is the use of a leave one out baseline estimate.
Okay.
Traditional PPO often relies on a separate value network to estimate how good a particular state or action is.
Right.
But these value networks can be complex, slow, and prone to errors, especially when you're dealing with the high-dimensional data we often see in language models.
So they ditched the value network entirely.
Exactly.
What did they replace it with?
They went with a more elegant approach.
Okay.
The leave one out baseline estimate, as the name suggests, looks at the performance of all the other rollouts for a given task and uses that information to establish a baseline.
Okay.
This allows the algorithm to more accurately assess the relative performance of each individual rollout and adjust the agent's policy accordingly.
So instead of comparing an action to some abstract notion of value, it's comparing it to how well other versions of the agent performed on the same task.
Right.
It's like a built-in competition pushing the agent to constantly improve.
That's a great way to put it.
Clever. What about the second modification, per token clipping?
Yeah.
What's its role?
Per token clipping is all about maintaining stability during the training process.
Oh, yeah.
When you're updating the parameters of a large language model, especially in the context of reinforcement learning, there's always a risk of making too big of a change and destabilizing the entire system.
Right.
Imagine oversteering a car.
Yeah.
You make a sudden sharp turn and end up spinning out of control.
Okay. That's a visual I can definitely understand.
Yeah.
So per token clipping acts as a safeguard, preventing those dramatic swings in performance and ensuring smoother, more efficient learning.
Precisely.
Okay.
It's like adding those guardrails to the learning process, keeping the agent on track, and preventing any major derailments.
Another noteworthy aspect of LOP is that it doesn't require a separate value network, making it much more memory efficient.
Right.
This is a big deal when you're working with massive language models, which are already quite demanding in terms of computational resources.
Exactly. It streamlines the whole process, making it faster and more practical to train these interactive agents.
So not only is LOP more efficient in terms of learning, but also in terms of resource utilization.
Yeah.
That's impressive.
This efficiency is likely a significant factor in why LOP was able to achieve such remarkable results with a relatively small training data set.
Okay.
It was able to extract every ounce of learning from the data it had.
It's all about quality over quantity,
That's
right?
exactly.
Now, I know our listeners are pretty tech savvy, so I want to touch on a point from the paper that I found intriguing.
Okay.
The choice of importance weighting.
Right.
They experimented with different levels per trajectory, per turn, and per token.
Yeah.
What did they find worked best and why?
That's a great question.
Yeah.
It gets to the core of how LP learns from the agent's interactions with AppWorld.
Okay.
They discovered that per token importance weighting yielded the best results. This means that the algorithm assigns a weight to each individual token the agent generates, rather than evaluating entire turns or trajectories.
Okay.
It's a very granular level of analysis focusing on the smallest unit of language.
Interesting. So it's like examining the agent's thought process under a microscope.
Exactly.
Okay.
This granularity is essential for accurately assigning credit and blame during the learning process.
Right.
By understanding which specific token choices led to success or failure, the agent can fine-tune its policy and make more informed decisions in the future.
So it's not just about what the agent does, but how it arrives at its decisions.
Precisely. Now, while all these technical details are fascinating, let's zoom out for a moment and think about the bigger picture.
Okay.
What does this research mean for the future of AI agents?
Okay, so what are the broader implications of this work? Where do we go from here?
Well, I think this paper paints a very exciting future for AI agents.
Okay.
We're moving beyond simple chatbots and basic assistants toward agents that can truly understand and interact with these complex digital environments.
Yeah. Yeah.
Imagine agents that can book your travel arrangements, manage your finances, or even write software code, all with minimal human intervention.
That's a future with incredible potential.
Yeah.
But like with any powerful technology, I imagine there are some challenges we need to consider.
Of course,
Can I
as
just
with
get a-
any powerful technology, we need to be mindful of the ethical implications.
Right.
And ensure these AI agents are developed and deployed responsibly.
Right.
But the potential benefits are enormous.
Yeah.
We could be looking at a world where many of those tedious, time-consuming tasks we handle are automated,
Yeah.
freeing up human time and energy for more creative and fulfilling endeavors.
It's a future where AI isn't just augmenting our abilities, but truly collaborating with us,
Yeah.
working alongside us to achieve common goals.
Precisely. And this paper is a significant step in that direction.
Now, I know we've covered a lot of ground, but I want to leave our listeners with one final thought. The agent's ability to learn those complex behaviors, like consulting documentation or recovering from errors solely from a task completion reward, is remarkable.
Yeah.
It wasn't explicitly programmed to do those things. It discovered them on its own through trial and error.
It really highlights the power of reinforcement learning to shape not just actions, but also what we might call problem-solving habits in these AI agents.
Right.
It makes you wonder, what other types of implicit knowledge could agents acquire through this type of training?
That's a great question.
Could we train them to develop even more human-like problem-solving skills?
Yeah.
Things like breaking down complex tasks into smaller sub-goals, or even seeking out new information when they hit a roadblock.
Those are fantastic questions, and I think they open up exciting avenues for future research.
Yeah.
What's particularly exciting is that this paper isn't just about improving performance on benchmark tasks.
Right.
It's about understanding the fundamental mechanisms of learning and intelligence in these AI systems.
Yeah.
And as these agents become more capable and integrated into our digital lives,
Yeah.
this understanding will be crucial for ensuring they work effectively and safely alongside us humans.
Absolutely.
Right.
We need to make sure they're not just efficient, but also aligned with our values and goals.
Yeah.
The last thing we want is to create AI systems that optimize for the wrong things or make decisions that are harmful or unfair.
So as we continue to push the boundaries of AI research, this is essential for guiding us towards a future where AI benefits humanity,
Yeah.
both in terms of practical applications and in expanding our understanding of intelligence itself.
Absolutely.
A pretty amazing time to be working in this field.
It really is. It's not just about building better machines. It's about understanding ourselves better in the process.
Well said. I think that's a perfect note to wrap up this deep dive.
Okay.
A huge thank you to our expert for breaking down this groundbreaking research.
It's been a pleasure. Always a thrill to discuss these cutting-edge advancements.
And to all our listeners out there, keep exploring, keep questioning, and keep pushing the boundaries of what's possible with AI.
Absolutely.
Until next time, happy learning.